here in mass transport, we're tracking down individual chemical species as opposed to the entire phase. So we're actually kind of zooming in what we were calling a phase, that we looked at the viscosity of water or whatever it might be, and now we're actually zooming into the water and looking at some individual chemical species that kind of might be moving on their own depending on the concentration gradients. Okay? So that can happen on top of all of the other transport that we talked about. Okay? So there's some slightly specific notation that we were using. So just a brief review. Let's see. My system is working. So just a brief review. So mass transport. Brief review of notation before we continue with the. We have just a couple of PowerPoint slides to finish, and then I'll be writing most of the day today. But I do want to do things by hand and not just flash the PowerPoint. So just a brief review. What did I refer to as row A? So this is my species A, and that species A has mass, and I divide it by volume. So I actually just go into individual molecules of A and look at their mass. So this is the same, it has the units same as density. So if I had a system, so basically this is density of species A. And if I had a binary system with only two, then basically row A plus row B plus however many I might have would be equal to what I'm accustomed to call density. More importantly, we will actually normalize this, and we will work with mass fractions. So my omega A mass fraction is rho A divided by rho. So this is just a number in between 0 and 1. And then omega A plus omega B has to be equal 1 when I divide my first equation by rho. And we will also talk about molar equivalence, because that's how often we are tracking chemical species. Just number of moles, the only catch there is that number of moles of something is not necessarily conserved while mass of it is, okay? Because if I have a chemical reaction, I go and track down individual molecules that change, so the number of them doesn't really, is not necessarily conserved. So I do have to look at mass when I'm looking at conservation. So molar concentration will be simply Ca, and that's number of moles of chemical species A divided by volume. So this is in mole per volume. And then again, my Ca plus Cb is going to be C, which is number of moles of everything. And we're going to talk about molar fraction, which is Ca divided by C. By the same token, we're going to look at the velocity, Va, which is my velocity of species A. And then I can do, using these fractions, mass fractions versus molar fractions, I can average velocity of the entire system using either molar fractions or mass fractions. So this is my velocity of species A. So then basically my mass average is going to be omega A VA plus omega B VB. So this is my mass average velocity. If you multiply all of this by rho, you're going to get, for momentum, remember that omega A is rho A divided by rho, so when you multiply by rho, you get this, plus rho B VB. And I could do I can use my molar fractions to average, and they can be slightly different. So that is my mole average velocity. And if I multiply this by C, then I will have in formulas CV star is CAVA plus CB BB. And then if I have a simple case where I don't have anything else moving, I have stationary, we had that slab of silica, and I impose my difference in concentration, then the law that is guiding this simple case is called Fick's law. So that is my equivalent of Newton law and Fourier law. Okay? So this Fick's law in the simple one-dimensional case, so I have Fick's law. In one-dimensional case, when I'm moving just in one direction, we had that JAY is equal to minus rho DAB, where my DAB is diffusivity, d omega A dy. So that is in one dimension. So this is my term that I'm going to be looking at. And we're scaling out rho because rho is my entire rho, right? It's not just specific to species A. And the units of DAB are meter square per second. So the units themselves are equivalent to that of kinematic viscosity, for instance, and the normalized thermal conductivity alpha. And in more general case, I have a vector JA that has all three directions, and that is minus rho DAB gradient of omega A. Okay, so this is my more general Fick's law. Now this is when there is no general movement of the phase, or I'm just looking at this movement relative to the entire phase. So my JA is defined relative to the movement, so it's rho A VA minus V, okay? So this is my velocity of the entire phase. So when the V, this velocity of the entire phase was 0, right? Or approximately 0, then I just had simple Fick's law and nothing moving around. But in most general case, I have to keep in mind that it's actually defined relative to it. Okay, so this is just quick review of notation labeled by writing as opposed to flashing PowerPoint. So I'm just going to now finish our... Yes? So rho A is multiplying V, okay? So it's basically that convection, right? There's stuff just moving in with V. So this has both molecular and convective components. So rho A VA, and I'm going to get back to that after this. Rho A VA is my combined flux that has both Fick's law, a Fick's law flux, and what moves in by convective. So both molecular and convective component. Okay. I'm going to get back to that. Let me just finish off our molecular origin of things. our famous molecular theory, by now we know how to sing it, I guess, for all of the formulas, because this is the third time we are seeing a similar situation. And the formulas we get in the end will be awfully similar to what we already saw. Everything is simple for a simple gas that is low density gas that we approximate only by moving balls that have only elastic collisions. So my kinetic theory, again, assumes that I have low density gas. These molecules don't have a lot of interactions, and when they do, those are elastic collisions, so I'm not losing any energy there. Also, at the same time, so my sort of momentum exchange is complete without energy losses. Also, I don't account for any intermolecular forces in here. And that is the most difficult thing to account for. And this is also the reason why for liquids, for instance, we don't have a good theory, if you remember, a good theory for viscosity. And the same will be actually true here. For DAB gets more and more difficult the more intermolecular forces you have to account for. Okay? And even these days, computationally, we are kind of getting there, or we can have these simulators. But these simulators, they can do up to 1 million particles, but we know that, well, billion, divide 1 mole of things by 1 million. We're not there yet. We're not there yet computationally, right? So it's hard to even simulate like 1 mole of anything in molecular dynamic simulation, because I need 10 to the 23, not 10 to the 6, right? That's just a couple of scales of difference there. But computationally, we're getting there. There are nevertheless insights from molecular dynamics, but they're not there yet. So in terms of kinetic theory results, we know that we have averaged formulas for mean free path between 2 collisions of these 2 balls. We also have distance between those, estimate of the distance, planar distance between those 2 collisions. And also average speed. So my molecules are moving around randomly oriented velocities, and their actual speed is given by this formula and related to macroscopic temperature. Okay? Now, frequency also, to derive the formula, I need to know what is the frequency of bombardment of how many of these molecules are going to bump into a plane from one side of it, because when deriving anything, I actually have to put a plane up and figure out, well, how many of these molecules are going upward, how many of them are going downward, and literally in this case, sum up the mass of them. Okay? So in mass transport, that part is simple. I'm not even looking at their momenta or anything like that. I'm just summing up the mass of everybody who is going up minus those who are going down. And one thing that we are in this process, we're imposing concentration gradient, okay? And I'm going to look at or relate it to this mass fraction omega. So again, I'm going to assume a simple Taylor's formula for omega. I'm repeating it once again. If there's one formula from calculus that you need to carry with you and always be able to employ, that is Taylor's formula. And typically you don't even have to do anything more complicated than first 2 terms, really. Anything more complicated complicates your any quadratic parts in there or second order derivatives complicate things much further than you'd like them to have complicated. So as long as you know the simplification of Taylor's formula, you're essentially good to go for most of the practical applications. So I impose my concentration gradient, and now I'm looking at my mass flux across a plane. Let's say that this plane is at y is equal to a. I'm going to look at all of the molecules crossing upwards. They carry with them everything from their last collision. So I'm going to assume that that's true for the mass fraction as well. And I have to reduce everything that is moving down. We know that we always, in terms of molecular movement, we're going to have molecules moving in all directions regardless of the applied gradients. It's just that because of the gradients, more of them might be going in one direction compared to the other. So I will simply count number of them and their mass, and that mass information will be carried from y minus a, those are for those going upwards, and minus those that are going downward, okay, that carry information from the plane y plus a. And now I have to note, so when I put actually what z is, z had that n, which is number per volume. Okay, when I do number of molecules per volume and I multiply that by mass of each molecule, okay, I'm gonna actually get density, right? Number times number per volume times mass is my total mass of them divided by volume. In my rho A, I want to relate to omega A because I have an expression for the for omega A based on the Taylor's formula. So my omega A, I remember that it's rho times, or my rho A, I remember that it's rho omega A. And that's essentially what we need here for this derivation. Okay? When I plug it in, I'm going to now have average velocity, rho omega A. And now I use my Taylor's formula for omega A at y minus A minus omega A at y plus A. And that is minus 2A times the derivative of omega A in y direction. Right? So when I put that in, okay, I now just simply write down what my A is, put it all in, and I indeed get that my mass flux of these molecules of type A, of species A, is minus rho, this is the entire phase, times some coefficient that depends on average velocity and mean free path for this type of molecule. And those I know already, they depend on the temperature, right? Macroscopic temperature, and things like diameter of this molecule and its mass. So something that is very specific just for these molecules and nothing else. And then outside of that, I have my derivative of mass fraction. So basically that is precisely what Fick's law suggested. So this is independent confirmation of Fick's law formula. And when I compare it to Fick's law, then this 1/3 U average lambda is essentially my dA. I don't have B here, we didn't consider B, so dAA, okay? Okay, so I'm diffusing in the molecules of the same type. So it is 1/3 U average lambda, and when I put in all of the formulas, I will get this expression. What is important here to remember is the dependence of square root of t. And I do have 1 over density here. Okay? So, and that is my density of the entire system. Right? So when I compare that to viscosity, it's that was the only difference that was dividing me for this type of situation, that is dividing me from viscosity. So just multiplying this entire thing by density, or this entire term here, is actually viscosity. And everything has this 1/3 average. So everything is molecular and very actually simple in this gas. Whatever it is that I'm trying to transport, I ultimately depend just on the average speed of this molecular collision, molecules moving around, and how far do I have until I collide with another one. Okay, that essentially that basically informs all of the types of transport that might happen in this low density gas, which kind of makes sense, right? So whether I'm trying to move the entire mass, which is resistance to it is defined as viscosity, okay? Or whether I'm just trying to transfer some heat through, which is ultimately going through these collisions, or I'm trying to actually move some of the, I have concentration gradients and I'm trying to move some of the molecules A to equilibrate that concentration gradient. These types of transport have ultimately this molecular resistance that has the same origin. Okay. So one thing to remember is, well, I just actually compared it already. So my DAA scales with square root of t, okay, just like we had before. And we don't have explicit dependence. Well, we have some dependence of pressure given that I have 1 over rho in there. Okay? So there are some corrections to it. So again, this 1 over rho can actually bring in the entire pressure of the entire phase into the picture. So that's something to remember for DAA. Okay, so what are now the corrections? We're not going to go into derivations, but just know that in order to account for different species A and B, this is the correction. I still have the square root of t right there in the formula. Where's my mouse? My mouse is not responding. But you can see square root of t dependence up there. And I have to do a harmonic average of the mass, and I also have to average my diameters. Okay? Now, in order to add intermolecular repulsive or attractive forces, there is a Chapman and Skog expansion, and it's applicable here as well. All I want you to really know is that there is a formula in there. And my dependence on temperature becomes a little more involved, so I have square root of t cubed. And I do have pressure here that shows up. But since I had density before, that's not necessarily a surprise. And I would still look up those collision operators, omega AB. Okay? So if you compare that to what we had for thermal, there we go, mouse showed up, it woke up. There we go, yay. All right. So if I compare that to my thermal conductivity or viscosity, I see that I have essentially a difference here. I have square root of t cubed, and I also divide by 1 over pressure here. Pressure being that of in the entire phase, not the partial pressure. And here is my K only had square root of t. So this is basically averaging things from molecular scale up. So we actually see this is, again, this still remains an independent confirmation of observations of Fick's law. Okay, so I already commented on the dependence on pressure and temperature. So theoretical treatment for liquids is much more difficult. We're not going to go into details, but you can actually look into chapter 17.4 if you'd like to take a look at what's happening for liquids. And now we're going to move to shell balances. First, we're going to overview general formulas. And then after that, we're going to look at some problems. I will most likely solve in class 18.2 and 18.3, but I do encourage you to look at those solved problems in the textbook. Okay? And just like before, for every steady state problem, we can either do shell balance or simplify equations of change, which we are we're gonna review those first before going to solving problems. Okay? So again, just like it's a similar thing that we had before, we could either do shell balance or your equations of change are essentially a shell balance, just accounting for time. So let's go and review those formulas. Back to a little bit of writing. So my macroscopic equations of change for multi-component system. So if we're going to generalize formulas a little further, though ultimately we're always going to really work with binary systems, but I want to write formulas in more general way. So this is your chapter 19.1 for your reading pleasure in PSL. So in general, I might have n species that I refer to with alpha. Not only 2, but in general, I have a mixture of n chemical species. And then my rho alpha is mass of each individual species divided by V. And sum of all these alphas is rho. And by the same token, then sum of all of the omegas has to be 1. So I have my rho alpha, alpha here, omega alpha, C alpha defined as just I did before. I already hinted at the combined mass flux of species alpha. We're going to refer to that as N alpha. Mass flux of alpha. Yes? C, omega alpha, C alpha. That's the molar fraction. Moles, number of moles per volume of alpha. And then X alpha, there's also X alpha, is the normalized, that's the molar fraction. Welcome to me writing alpha. You're going to be looking at this entire class. Get used to it.
These A's are supposed to be alphas, right?
Yes. I corrected one.
Don't worry, in Greek alpha I say.
In
Greek alpha I say.
Yeah, but I just needed another symbol. That's all. Yeah, I'm pretending to speak Greek here. Thank you. So A and alpha are the same thing. If I were Greek for A, I would write down alpha. So there's that. Okay. Though this alpha is lowercase, what is uppercase alpha is still A, isn't it? Does anybody speak enough Greek to confirm? Because I think this alpha is lowercase alpha, and the uppercase is still A. So yeah, not a good save. All right. Anyway, where were we? So this combined mass flux is going to be my change color. My Fick's law flux that looks things relative to the movement of the entire phase, just due to the concentration difference, plus the convective part, and that's whatever moves with my entire phase. So my sum of my alpha just moves in because it does. Okay. And recall that my velocity is that mass average velocity. So it kind of averages all of the different species using their fractions. And the equivalent of this for molar flux is going to be uppercase. The difficulty of mass transport is just keeping track of this alphabet soup. A, B, uppercase, lowercase, C, omega, X. Just take 10 minutes just to kind of repeat those 5 times to get used to them, quite literally. Like keeping track of all of the notation is the difficulty. Huh? Yes. You see, this is a test. This is just a test whether you're paying attention, right? Because at the beginning of the class, I introduced it as A, and now I have to switch to this more general notation, and my brain is saying no, inertia. I'm staying with A. Hey, combined molar flux also of species alpha, and I'm gonna use stars, okay, to refer to that. So it's uppercase J star plus C alpha V star, and my V star is the average using X's. So this NA is really rho A VA. And this is really CA VA star. And one thing for general formulas that I'm gonna also take into account is my R alpha, and that is rate of production. I might have chemical reactions, and I often do. It's, as a matter of fact, when I have chemical reactions that I need to track down individual chemical species most of the time. So I have rate of production of species alpha. So this rate, it's kilograms per meter cubed second, and its molar equivalent is R alpha. Yes?
Flux J is
That's
why is the same as the rho alpha V alpha? Because then J should be general.
So this is my molar only, and this is what moves with the entire species.
Yeah, but you can equate rho alpha and V alpha.
You can actually plug it in here, okay, what a V is. You also have to account for the fact that J alpha plus J, well, sum of all J's is 0, okay? That's what's going to help you out in this. Okay, so now we need to do equations of change. We need to balance something over a volume. So let's just draw, or should I just draw? Well, I'm going to draw here and then write. So this is my volume. So if this is my box, and it goes x plus x star L, x, then there's y, x, and z. So if now I'm looking at what is getting transported in x direction across these sides, my combined addition of species alpha through these faces in x direction is basically n alpha dot dx, right? evaluated at x is basically rate of addition of species alpha across this green phase, right? Combined addition across phase x, which is my green phase, right? And I would just evaluate it at x plus delta x, really. And at x plus delta x, I'm removing it, right? So n alpha, whoops. N alpha evaluated x plus delta x, that's removal at x plus delta x. And that's my red phase. So just like before, in order to enter any kind of volume, I gotta go normal through the surface of the volume locally. Yes?
Earlier on, sorry, just to check, is that rho alpha, V alpha, and C alpha, D alpha star in the red?
Yes. Yeah. I obviously don't speak Greek, I speak Croatian as my second language, or first rather. Though it was actually my Calculus 3 professor that forced me to learn Greek alphabet. So he actually, as part of the whatever, multi-dimensional or multivariate integration formulas or whatever, he would actually quiz us on Greek alphabet. Like, for math, you need to know Greek alphabet because we keep using the weird. And the other one, where else did I do? Oh, yep. So again, I did not learn any Greek, but it was my math professor that forced me to learn Greek alphabet, and that's. I did have 2 years of Latin though. All right. All right. Let's balance things. We're ready. Notation-wise, we are ready. So now, if I'm looking at the rate of change of mass, so rate of change of mass of alpha in my volume defined by that box x plus delta x, y plus delta y, z plus delta z. How would I translate that into the terms that I just, rate of change in time, should I say? dm and that is actually d rho alpha dt. Since my volume is not changing, I'm gonna write down what it is because I'm gonna be dividing by it. D derivative, these are derivatives, these wiggles. Derivative in time of m alpha. And it's the derivative of density times volume, right? And volume is not changing, so I can just scale it out. Now that change is due to what enters, what's added or removed through the sides, right? So if I look at my x side, what is the total stuff that enters my side? I have combined flux. How did I refer to it? N alpha. And I have to dot it with delta x, with my x direction, right? So it's really just N alpha x evaluated at x. Now flux is normalized by the area, so I gotta multiply it by area. And what's removed on the other side, other x side, is minus N alpha x at x plus delta x. And again, both are multiplied with the area of the side. Yeah? And again, once you're kind of familiar and accustomed to the notation, this should be easy to write down. Once you get your Greek alphabet down, okay? So now we just repeat this for x sides. Now I do for y and for z. Okay, so I'm just gonna basically alpha y evaluated as y. So again, this is a dot product of an alpha with the normal in that direction, which is delta alpha, right? Normal in y direction. And if I had some generalized normal, well, it would be some general normal to some whatever weird shape my volume is, and I would then integrate over the sides as opposed to just sum up 6 of them, okay? Because this is really integration over the sides. And this is that from calculus, speaking back to relate that to your multivariate calculus class, if you still remember any of it, this is that relationship between surface integrals and volume integrals and deriving partial differential equations. Again, because you have to count up and now, this is delta x, delta z as the area of the side in perpendicular to y direction, and then I just repeat the same for z. My standard, okay, this is it. And then one thing that I'm gonna add, I might have production term, okay? And that one was kilogram per meter cube second. So then I just have to get the rate of change, is I just gotta multiply it by volume, and it's gonna be kilogram per second. My standard procedure, divide by volume and take limit So what I'm going to get is d rho alpha dt is, so n alpha x evaluated at x minus n alpha evaluated at x plus delta x divided by delta x. When I take limit, then delta x goes to 0. I get minus d n alpha x dx, right? So here I have minus d n alpha x dx. Here I have minus d n alpha y dy, d n alpha z dz. This is my favorite operator. Divergence. Uh-oh. You still, it is almost December and you still don't know what my favorite operator is. We are in trouble. I did not teach you well. All right. And what's going to be left here is just R alpha. And this is true for every species alpha. So this is my equation of continuity for single species. Okay? And I'm going to break this down to components because my n alpha is combined. So it's really minus divergence of J alpha minus divergence of rho alpha V and plus R alpha. So this is just my diffusion as per Fick's law, diffusion only.
What is that?
J.
Oh,
Unfortunately, for the rest of the week, you will have to endure my handwriting. Because we're going to start solving problems after deriving this formula. This is my diffusion. This is my convection. Right? That's just simply what moves in by movement of the entire phase. And this term is production. Now, if I sum up, so I need to sum up all of the alphas. What will I get? What do I expect to get? What do I have to get? Regular continuity equation. So basically, we're going to finish that next time. But basically, sum of all of these will be 0. Sum of all of these will be actually end up being my divergence of rho v. Okay? And sum of all R alphas is 0 because of the mass conservation. So if something is getting produced, something else has to go away. So essentially, that's going to give me my continuity equation. All right, we're going to continue next time, and we're going to, well, we have a couple of more formulas to review, and then we start solving problems.
Oh.